Hello and welcome to a new coding challenge video. Today, of course, we will see the solution to coding challenge number 23. Now, I should point out today more than ever that the solution I'm about to present is of course my own, and you might have indeed found better or simply different solutions. So feel free to take the solution I'm about to show you today and improve it with your own ideas. Now, the approach we will look at today involves analyzing each pixel, and for those which are white, namely have been obscured, taking the topmost, bottommost, rightmost and leftmost pixels which are not white, and averaging their values in order to determine the value that that pixel should now have. Of course, this will make the overall picture a little blurrier compared to the original, but it should at least let us see what the general theme of the picture was. So first of all, before taking any averages, we have to write 4 separate functions which will allow us to get, as I said before, the topmost, bottommost, rightmost and leftmost non-zero pixels. We can start with calculating the topmost non-zero pixel by writing define get top non-zero. Then we will give it as arguments an array which will be our image, as well as the x and y coordinates of the pixel we're currently analyzing. Then we will say, of course, if y equals 0, meaning that we are analyzing a pixel in the topmost row, of course the topmost pixel will be the pixel itself, because we cannot go further up than the top of the picture. So we will say return 0. Else, we can say for I in range 1 to y plus 1, we can say if array y minus I, as well as x, because remember when we are addressing an array, we give it the y coordinate first, followed by the x coordinate. And we can say that if this is different to our obscuring value, which of course, as we remember from before, is 255, we have that written in line number 6, we can say return y minus I. Else, if for none of those cases, the array, or the pixel to be precise, is different to our obscuring value, then we have to return the topmost pixel, which is 0. Now this is the basis of our analysis in finding the topmost non-zero, or in this case non-white pixel, in order to then calculate our average. I trust that the structure of this function, if you've followed my tutorials so far, shouldn't be of a particular challenge to you. However, should you have any queries, then feel free to let me know in the comments below, and I will do my best to answer them as soon as possible. We can of course use this same structure, albeit with a few tweaks, to write out 3 more functions which will allow us to get the bottom, left and rightmost non-zero pixels. In this case, I've simply copied them here, so feel free to pause the video and copy out these functions into your own code should you wish to follow along with this solution. Now that we've written out our 4 functions to calculate the top, left, right and bottommost non-zero pixels, we can now write out the main function which will interpolate our values. We can start by writing out a tolerance value, and we'll see what this is used for in a second. And then here is our full interpolation function. We've called it advanced interpolate image, and we've given it an argument called new r, or new array. Now, as you can see, we iterate over the x and y ranges, so in the x and y direction of our image, and for each pixel we say that if the absolute value of the difference between the value of that pixel and the obscuring value, which is 255, remember, is smaller or equal to our tolerance, hence our tolerance value, then we go ahead and do the interpolation. Of course, to get the x and y coordinates of our top, left, right and bottom non-zero values, we use the 4 functions we wrote out before. So get left non-zero, get right non-zero, get top non-zero, and get bottom non-zero. And we call these four values LRTB. Then of course the average value for our pixel will be the value of each of the pixels in those given coordinates. So TX, BX, so bottom, so top, bottom within the same X coordinate, and then YL and YR in line 72 and 73, which means the leftmost and rightmost within the same Y coordinate. Of course, all this has to be an integer division by 4. And that will give us the new average value for the pixel we have in question. The last thing we do in line 74 is to assign this average value to the pixel in the y-x coordinate in order to complete the interpolation. Of course, once we've interpolated over the entire array, we return the new array. Now, as a last step, in order to complete the iteration over our image, we need to write out one further command, which is iterations equals, for example, 8, and then we say for I in range iterations, then we can say new array is equal to adv interp img of new array. Then new underscore image will be image dot from array of what? Of new array. And as a last action, we can say new underscore image dot save, and then we'll give it a name, for example, image.jpg. Oh, and of course, I forgot to mention that new array is equal to numpy array of image dot open our obscured image. So obscured underscore img dot jpg. Oh, and of course we can't forget the tolerance value, which at each step we can increase by 15, for example. We can now run the code, and you can see that the image we've created is, yes, a bit dark and not perfect, but we can indeed start to understand what this is actually representing, namely, of course, the Mona Lisa. There are, of course, a billion other ways with which you can refine the image and create a clearer render. This, for example, is a result I obtained using another piece of code which I created, which unfortunately didn't make the cut when creating this video. Of course, I'm sure some of you also obtained much better solutions, and I invite you therefore to share your code down in the comments below. I look forward to seeing what you have come up with. As usual, I thank you all for joining me today again for another coding video, and I look forward to seeing you all again next week. Until then, please don't forget to like, share and subscribe, and as always, happy coding!